I will take you through some of the optimizations that JVM do. And most of these optimizations are true for any other languages or even for the operating system. Okay, so even if you will see the optimizations that your Linux operating system do, or your Mac OS or Windows OS do, it's almost the same thing. What are the optimizations we do at the JVM level also? Okay. So what I will do is that we will discuss with something called speeding up the Java application. Okay, and we'll get to know that how actually we improve the performance of the Java application. Okay, because as you all know, Java is actually an interpreted language, right? So interpreted languages are generally very slow. Okay, so any one of you have heard about JIT compiler, just-in-time compiler?
Yeah.
You can raise your hand so I can see. Yes, excellent. So I can see two of the guys raising the hands. Okay. And since I am seeing only half of the group, so I will do into two. Maybe 4 people are there. Okay. So what kind of things you know for the just-in-time compiler? How you have heard of this name, and have you used it sometimes in your application? Yes, please go ahead. I can hear you from there also.
Okay, so I haven't worked with just-in-time compiler. I do know that there was something called hotspot compiler based on the usage of the code. Some of the code will be translated into x86 and it will run. Okay, that is what pretty much the idea which I am having.
Okay.
So I worked with bytecode engineering language in the past, so I do know how Java bytecode works. So that is pretty much my answer.
Okay, excellent. So yeah, that's quite a good, actually, you know quite a bit about the just-in-time compiler. So Java have actually 2 compilers. One is the Java C compiler, which is actually a very dumb compiler. Okay, which don't do anything. It just parse your .java file and convert that into a class file, right? And then there is something called runtime compilers. There are 2-3 runtime compilers in Java, which many times we name as just-in-time compiler. Okay, so we will go into the detail and we will see that what runtime compilers actually do and how it optimizes our code. So again, saying that if you have question anytime in the presentation, please raise your hand and I will stop there. Okay. Right. So okay, from the Oracle, there is a disclaimer that whatever I am saying is just my words. It has nothing to do with Oracle. Okay. Okay. So we will see the Java execution process, and then we will see Java interpreter and the runtime compilers, and definitely the optimizations done by the compiler. And when you do optimization, you have to de-optimize also many times. And what are the impacts on the real application? Okay, so some of the real applications we will discuss, and we'll see how it is complicated for the benchmarking, right? So it's tough with all the optimizations to do the benchmarking. Okay, and the QA which I have written in the end, it can come at any place. Okay, so feel free to ask questions. All right. So this is a very small Java execution process, which is very easily understandable by most of us. There is a .java file. By Java C, we convert into a .class file, right? And that .class file, we give it to the JVM process, which have a Java interpreter, which has a just-in-time compiler, okay? And then we get something like native code, and it deals with the native operating system. So our main focus today is actually the JVM, right? So as I have promised to Swal that we will discuss about a bit of JVM here, right? So what I will do is that, okay, let me see. Probably you can see my browser, right? So in my browser, I will just go to in my browser, I'll go to the source code, and there is source code, and there is a VM source code. All right. So this is pretty. Probably you can see my browser screen, right? And this is pretty much what actually the JVM have. Okay. And the interesting part of this is you can see the folders for the garbage collector. You can see the folders for the memory optimizations, I mean memory management. You can see some of the folders like runtime. And there is folders like OPTO, which is called optimization folder. Okay. And you can see C1 folder and lot of compiler folders. So we will definitely discuss about, yeah, please.
Can you just increase the font size a bit?
Yes, that is the quite, okay, let me see if I can, Fine now?
Bit more.
Bit more, okay.
Yeah, okay, fair enough.
Okay, right. These are pretty much simple things. So you should just know that whatever this folder contains, there is something for the garbage collector, there is something for the memory management, and there is something for the runtime compilers. Okay. And there is something for the assembler, which is ASM. Okay. Now the interesting part is that what happens. Okay. So what any one of you have ever run a program with just Java interpreter? You know how to run a program in just Java interpreter?
Yeah.
How?
So did you mean, okay, so you compile and then you call the Java with the command line argument, you have to give the main class to execute that. Did you mean that?
Please come up again.
So you invoke the java.ac and along with it the class name which contains the main.
Okay, so yes, let me show you that. So what you are saying is that, okay, you want me to increase this font as well?
No, it's
Okay,
yeah.
okay, excellent. So I have a very simple program, say like hello world.
Okay, so
Just
compile using Java, hello.
Cut it. Okay, so yeah, I will just show you simple things. So what we do is that say like I have a code like this. So you did this, right? And that's a compiler. And I will definitely show you what is written inside this code. So nothing is written. Okay, just think that it's a hello world. Okay, right now I have written something. So then what you do is you do this, right? And this code runs. So this code actually don't go to only interpreter, okay? Because this code gives you the interpreter plus compiler both. Okay, I'll show you the difference. So what I am doing actually in this code is I am taking the time at the beginning and then I am doing some calculation here. Here I am doing some simple calculations and then I am taking the time in the end. Okay, and I am just saying that whatever the difference in the time, right? This is a typical way we write the code, which is not actually a good way, but let's go for that. So what I am doing is that I am saying that tell me that how much time it takes to run this code. Okay, and I am running this continuously and you are seeing the time, right? So it's taking some different time just because it's doing different work. Now what you can do is that you can pass something called -xint. Okay, and when you pass -xint, it says that I will only run the interpreter. There is no runtime compiler, that there is no JIT compiler that will come into the place. And then I will run the code and you can see the time, right? You can see it's taking huge amount of time in comparison to the previous value, right? Like this only, there is something called -xcomp, that is called comp, that says that it will always run into the compiler mode, means it will never go to an interpreter. And if I run the code now, you can see the time, right? So probably you can see it's pretty much better than what the only interpreter code was doing, right? And what actually, yes, please.
Couple of questions.
Right.
So when you gave -xint, okay, so we were getting more time. So that means they were executing Java bytecode, right?
Yes.
So do they do ahead of time compilation in the case of -xcomp, because there was a delay initially?
What -xcomp do is that it takes the control from the interpreter and it gives the control to the compiler. And why it do the things faster and why it do the things slower at the first time, that all thing we are going to discuss today, right? So you must have seen that there is a slow startup and you must have seen that there is a speed after that, right? This is what you are asking.
Yeah.
Right. Yes, I will show you. I will show you that. Okay. And if I'll just do Java minus version, you will see a thing that is called mixed mode, right? So what this mixed mode do is actually there's a mix of interpreter and compiler. So when I just run this code without any xcomp or xint, okay, when I run this code, then it is actually something called -x mixed, which is which is the default way of running the code. Okay. So we will discuss in the detail what is x mixed, what is xcomp, what is xint, why it took a slow startup, why it was faster after, all the things we will discuss. Okay. Right. So what happens that okay, let me do full screen also. No, but I want to see you guys also. So this is visible, right? I don't need to do full screen.
Yeah, it's visible.
Okay. Yeah. Okay. So runtime compilers have two parts. Okay. And why there are two parts, you need to understand. It is possible that you are running an application which has lot of UI. Okay. And one part is possible that you are running an application which need faster services like your transaction, like your bank transactions, right? So there are two phases for the compiler. One is the phase where compiler says that I cannot go and optimize my code too much, because if I'll optimize the code, it will be slower. And when it will be slower, it will not render the UI so fastly, right? So what will happen that you are loading a UI and it is stuck in between, right? You will not feel good, right? You are loading some kind of game and it is stuck in the middle, right? So it will not look good. But there are a lot of places, like when you are doing the banking transaction and all, you are saying that it's fine to be slow for the starting, but after that you should give me a very good performance, right? So on the basis of this two, what we did, we made two compilers. One is called C1 compiler and one is called C2 compiler. C1 compiler is called client compiler. Client compilers are generally for the UI thing, okay? And C2 compiler are server compilers, which we use for the server work, okay? Means the non-UI jobs. And in JDK 7, we came up with the idea called tiered compilation. Okay, tiered compilation, what it do, it actually mix C1 and C2. So let's not go into the detail of tiered compilation right now, but what we will do is that we actually mix C1 and C2. Okay, so from this slide, the understanding is that we have something called runtime compilers, that is called JIT. In most of the common people use JIT, but there is nothing called JIT. We just put a name for the outside world. The actual thing that happens is that there are two compilers. One is called C1 compiler, one is called C2 compiler. Both are runtime compilers. So it has nothing to do with Java C. It has the work to do after Java. Okay. Now, what it do is that, okay, sorry. It do a lot of optimizations in the code. So whenever your code will be submitted, to Java command, it will look for what kind of optimizations that can be done in your code. Okay. So let me take you through some of the optimizations, which few of them are, few of the optimizations must be for the first time for you. Okay. So you will feel interesting optimizations that happen. Okay. Like this is the one of the example called dead code removal or expression optimizations. So you know that most of even IDEs these days remove dead code for us, right? So whenever you will write the code in IDE and you will leave some dead code, the IDE will tell you that there is a warning here. This is dead code. So if you see the box which is on your right hand side, probably can you tell me what is the dead code on that side? It's very easy to predict, right? So yes, so you can see the result 3 is a dead code, right? Because we are not using result 3, right? So what the JIT compiler will do, it will straightforward remove that int result3 equal to x1 plus x3. Okay. The second thing, you can see that this code can be optimized. The expression can be optimized, right? Because it is x1 plus x2 plus x1 minus x2. So x2 and x2 can be cancelled, and it is finally x1. So your complete code will be converted into code block 2, what I have written, right? So when the JIT will go for the optimization, it will reduce the first block into the second block. Okay. So this is a very simple optimizations which most of you understood, right? So I will take you through some of the more interesting optimizations. Okay. Most of you who are even from the C or C++ background, you must have heard about inlining of a method, right? So any one of you can tell me how you inline a method in C or C++? Any idea?
So you need to prefix the subroutine with inline.
Right.
Whenever you create.
Right. And who do that?
So the programmer has to explicitly do it. Okay.
Right.
Here it seems okay.
Right. So what happens in the C or C++ compiler, that programmer have to inline the method by itself, right? It is explicit inlining. But what we do in the Java, that the inlining is done by the Java runtime, that is the JVM, or you can say the Java runtime compiler, that is the JIT. Okay. So by default, any code which is smaller than 35 byte, okay, the JVM will inline that method. Okay. It's always good to inline the smaller methods, right? So why we do inlining, as most of you know that function calling actually is a costly operation, right? When you are calling a function, actually you have to save the stack pointer, you have to save everything into the stack, and then you have to transfer your control to somewhere else where you have to do all the work, and then you have to take the control back to the point where you have left it, right? So it's a complicated, time consuming job. Method calling is always a time consuming job. So we came up with the idea called inlining, right? And inlining is there from us from maybe 60, 70 years. But the problem with the C++ inlining, okay, is that the programmer need to inline, which is not a correct idea. Because a programmer cannot say that which method need to inline and which method not need to inline. I will give you a simple example, right? Think like you are doing the HR management job, right? You are doing the HR management for your company, and you have to say on 31st you have to calculate the salary of the people, right? So on 31st I need that method to run fast, which is actually calculating the salary. But for 1st to 30th of the month, I don't want that method to run fast because I will hardly call that method, right? So all the get calculate salary method will get called on the 31st, right? So Java do this. Java keeps seeing the method counts. When a method count will cross a threshold, say like it will cross 5,000 time calling, right? Then the JVM will decide that this method is called something called hot method, which is the method which is called too much time. And then the JVM will decide that we should inline this method, because inlining this method will give us a better performance, right? So you can see whatever the code I have written on the left hand side, right? So I am calling a method, and here I can directly call inline the method, right? So I don't need to go with the whole concept of the method calling, and I can just inline the method. Okay, probably not a good example. I will show you a much better example. So you understood the whole idea of inlining a method? Any questions? Do you have any question in the inlining?
No, so far good, at least from my side.
Okay, so far good, right? So okay, I am taking your expression as the complete team expression. Okay, so because if you understood, and even if some of your member is not understanding, your duty is to explain them afterward, right? So that's perfectly fine. That's perfectly fine for me. Okay.
Yeah.
So okay, this is also one optimization which most of you know, right? So even in the C++ time we do the inlining. Okay, even the Linux operating system do inlining. Even the other than Microsoft operating system, I know all the operating system which do the inlining, and no one knows the MS code, right? So we don't know that. All right. Now, this is again one of the technique which is very simple. That is called caching technique. Okay, right? You all know that caching is very useful. And these days we are increasing the cache size because the processor size are limited now. The processor speed is limited now, right? So what we are doing, we are increasing the caches, L1 cache, L2 cache. And what happens that cache sits somewhere between your processing unit and between the RAM, right? So from your cache, the data can be taken much faster than what it will be taken from your RAM, right? So if in this example, you will see we are using something like p1.x, where p1 is actually a class instance, and p2.x, p1.y, p2.y, right? So what will happen if we will continuously keep using the value of p1.x and p2.x and all these things? What will happen? That the JIT compiler can understand that this guy is using this value very frequently, right? And what it will do, it will actually cache those values. Okay. Think like in the second loop, you are calling monitor.flag, right? And I am running a while loop on monitor.flag. Okay. So it is very good to cache that value, right? So what I will do is I will make a temporary variable called flag, and I will remove that flag into monitor.flag, right? So this is a simple caching technique which can which can improve your code. Okay, so this is also done by the JIT compiler, right? So far so good. Okay. Okay. Now, okay, we will come to uncommon trap. Before that, okay, this is very interesting. Any one of you know monomorphic calls?
Not much idea. Okay, so morphic. Okay, good. Non-polymorphic code.
Okay, yes.
Okay.
So you all must be knowing about polymorphism, right?
Yeah.
That's a good interview question. What is polymorphism? Okay, so you better know those questions. So polymorphism is something where you say that a method can have two different behavior, right? So I have a different method, and what I do is that I override the method right at the second place, and I will get a different behavior, right? And Java actually, by definition, supports polymorphism, right? If you need to do in this old compiler like C++, I will not say old compiler, but if you're doing it in through C++ compiler, you have to put a keyword called virtual, and then only you allow the methods to be overridden, right? So you all agree with me, right? But in Java, there is no virtual keyword that is required, because by definition, all the Java methods can be overridden anytime. Okay. But this is a costly operation. This is a costly operation because at the runtime, we need to decide that this method have only one call or this method have virtual calls, right? And it is possible that you are not calling the actual instance, but you are calling the reference to the other, right? Like if you have a parent and a child, so from the parent reference, I can call the child methods also, right? So at the runtime, I need to solve this problem, right? This problem actually is little bit of time consuming, but what JIT compiler do, that in case your method is a monomorphic call, right? You have just written a method once, and you have not overridden your method anytime else, right? So what you are doing, you are creating a monomorphic method, right? Say like I have an animal class where I have put a color, and the get color is giving me the color, right? So if I'll create the child called cow, say I will create Jersey cow. So Jersey cow color is black and white, so I will return black and white. If I am creating dog, I will return brown. I am creating lion, I will return brown. I will create, say, peacock, I will say multicolor, right? So actually what is happening, that your calls are monomorphic, right? I am not overriding this call. I am not actually changing the logic of the call. So what I can do is that in place of doing the complete call, I can remove directly by animal.color, right? And I can save a lot of time of the method calling, which is actually a virtual method call. You guys are getting me?
Yeah.
Okay, cool. So But what will happen if you are running your code consistently, and after say 20,000 of iteration, you will get suddenly something which breaks your assumption, right? Which breaks your optimization assumption, right? Because you are assumed that none of the method will go into polymorphism. Every method here is actually monomorphic, which you have optimized. So what will happen in this kind of case? At this kind of case, the compiler do something called de-optimization, which is very simple, right? So in the animal class, generally I used to give an example of say chameleon, right? So you all know chameleon actually change the color, right? So according to the environment, it can take some color, right? So what I have to do is that I have to write a different logic for an animal called chameleon, right? Where I will say, read the environment, and according to that environment, you have to set the color of the animal, right? So what happened is that my optimization, which I have done, actually need to go by a de-optimization process, because my rules of the thing got broken, right? So I have broken the assumptions that I have done. Okay. So for that only, what we do is that we put something in our code. We actually inject into the code, right? So that is called uncommon trap. And uncommon trap says that do optimizations. If optimizations will get failure, go by uncommon trap path. Means de-optimizing it back. Okay, so de-optimize will give your code back to the interpreter. Okay, so the runtime compiler will give your control back to the interpreter. It will flush out the optimized code, and which will start running back the interpreted code. Okay, so
So I got
just I will explain you this code, and then I'll take this question, right? So in this question, I am saying int result, if var is greater than 5, I am saying compute var. Else I am saying result equal to 100, right? Now say that it will never happen that var is actually greater than 5, right? So what I will say is that I will directly make the value as 100, right? But I will say that if var is greater than 5, probably I have to go by a de-optimization path, and that is uncommon trap. Okay. Okay, please go for your question.
Okay, so my question is, okay, what I have understood so far is, since Java has got the default option of always override, but when you load a class, okay, you can actually inspect the hierarchy and understand that, okay, we are always making monomorphic calls, okay, you will go for some kind of an optimization. So my question is, whenever a new class is dynamically loaded, so will you have a pass which actually check all the assumptions, or it will take time, right?
Yes. So when you are loading a method dynamically, right? Still, we need to tell the JIT compiler that go and check the class hierarchy, go and check the method hierarchy. If the method hierarchy is broken, the JIT have to de-optimize the code whatever it has optimized.
Okay, and the second question is, okay, how will you understand that var won't be, say, go more than 5 or something? Okay, so how you take that decision, okay, from the source code?
Okay, in this case, right? So what happens that I don't have to understand anything. What will happen that your server will your Java process will start, right? Your Java process will keep seeing the count. Whenever it will call this method, it will keep seeing how many times I am going to the if condition, how many times I am going to the else condition. So it will have a threshold. Like for the JIT compiler, C2 compiler, the threshold is 15,000, which is a default, which can be changed by anyone, right? So it will say that for the 15,000 time, this guy is going into the else condition only. That means it is the right time that I should start doing the optimization. Maybe this guy will never go into the if condition. Okay. Though even these values are coming at the runtime, if by mistake it will happen that it will go into if condition, I have to de-optimize that code. Okay. But think that in the 99.9% of the time you are going to the optimized loop, then you are just throwing out a if else condition, right? So only 0.01% of the chance that I will go into a de-optimized case.
So, okay, one last question regarding this. Okay, so when before you go for JIT, okay, you need to run your routine at least 2,000 times or 3,000.
Yes, yes, yes.
Based on frequency, you understood that it never goes more than 5. So you generate the code in such a way that there is uncommon trap. So my question is, when will you evaluate, or okay, will you inject uncommon trap during the JIT time, or after you have JITted, okay, you will actually re-evaluate the thing once you understood that after 15,000 still he's not going above 5, so I can safely do that. What is the system?
Right. So your voice got a little broken in the middle, but what I understood is that you are asking that when JIT actually inject the uncommon trap, right? So there are a lot of things which can be resolved at the static time, like say the dead code, but there are a lot of cases like this code, right? So what happens that we inject the uncommon trap when we do start doing the optimization, right? And optimization for any compiler starts when it actually get heat up. Okay. So for the heating of the compiler, you need to run compiler for a very longer time, right? And that is the true case, right? If you are running the servers, okay, some of the servers which we are running from say 10 years, last 10 years, so it is totally optimized. It actually understands which method need to optimize and which method not need to optimize, right? So you will have a slow startup. Okay, you will have a slow startup because you will have even more slower startup than a unoptimized code, right? Because unoptimized code directly have to start running your codes, but a optimized compiler have to give time even to learn the optimization, right? So what it will do, it will optimize, it will de-optimize, it will optimize, it will de-optimize, and finally it will have the profile information, right? You all know the profiling information. It will have the profile information according to which it will understand that, okay, now this method is the right method to optimize. Okay, so I will inline this method, or I will go by a uncommon trap, or whatever the ways I will take. Okay, so there are multiple things which we do, right? Is that I have answered your question?
Yeah, sure, you can go ahead.
Okay, cool.
Yeah.
Okay, one of the most beautiful optimization that I am going to see you is now actually something called null check. Okay, this is one of the most complicated optimizations that we do because okay, so there is a question for you. What will happen if x equal to null and you will try to do a C out or C in a C++ compiler? So what it will lead to what?
It will actually, okay, since there is no runtime in this case of C++, it will crash the program.
It will crash the code, right? So you will end up getting a segmentation fault, if I'm not wrong, right? That is called SIGWI signal, which is a signal generated by the operating system. But what will happen in the Java for the same?
See, in the case of Java, okay, so there is something called checked exception. Okay, I've heard about it. Okay, so
okay,
what I feel, JVM can catch it. Okay, but based on the policy set by the environment, okay, it can actually take decision. Okay, that's what I know.
Mm-hmm. Yes, so you have studied correct, and what will happen in the Java is that in a normal case it throws something called null pointer exception, right? So you are pointing somewhere null and you are trying to use that value, right? So you will end up having a null pointer exception, which is very well thrown by the Java compiler. Okay, so now there is a beauty here. Okay, it may be little tough to understand, but you can understand that. You are trying to access a memory and something is not available on that memory, right? Still not getting a segmentation fault and throwing a null pointer means we have done something fishy, right? So what actually we do is something which is mentioned in this slide. So if I am creating instance point and I am using point.x and point.y, so for every instance variable, what Java do is that Java will take if point double equal to null, throw a null pointer exception, else x equal to point x and y equal to point y, right? So you can understand for all the instance variable, actually Java inserts a if else condition. Okay, you got the point, right? And you can understand that this is such a tedious job, right? In a normal small to medium size application, you will have more than 4 lakh or 5 lakh actually instance variable, right? And what you are doing with all the instance variable is that you are inserting a condition there, right? So this actually makes Java code little bit slower. Okay, But what we do, you can see that here the JIT have a scope to optimize. So what JIT will see, that JIT will keep running your code and it will see the instance variable is not going null for this guy code, right? So whatever the code I am running, actually it's never happening that I am getting an instance variable null. So Java will throw the NPE code, right? Java will tell that I will use x equal to point x and y equal to point y directly. And if there is some problem, I will put an uncommon trap. And I can explain you the complexity of this uncommon trap, because when you will throw this if-else condition, what will happen? Your code will go for the segmentation fault, right? But before going to the segmentation fault, the JVM will take the control. It will tell, no, there is something wrong which I have done. Let me check it out. And it will again go and put the if-else condition. That means it will put a null pointer condition. So it's actually a complicated thing, but by throwing the if-else condition, actually JIT can optimize. And that's why in our best practices, we always say that you should always have control on your data structure. So if your data structure is going null almost many times, sorry. So you need to see your data structure, that why it is keep going null. Don't keep just putting the condition, okay, if null then do this, if null then do this, right? Because the data structure which you are using should be totally under your control. And if you will go to the new languages, like the new languages that came on the JVM, like Scala and Go and the Kotlin. So if you will see, 1 second, I will show you, right, probably, sorry, just hold on. I will show you what these all new languages do. Okay. So I don't know any one of you have worked in the Kotlin or Scala or some other new languages, but in Scala, in the Kotlin, if you will say int C, not int, sorry, integer C, okay. And if this C possible to be null, right, it will not allow you to write this code. So you always need to write if C double equal to null, do something, else use the code, okay? Because these compilers leverage the complete optimizations that JIT do. You are getting my point, right? It's not so complicated, I think. So yeah, the basic thing is that you got the idea that how a null pointer exception can be optimized. So what we learned in this slide, that how null pointer exception comes at the place, and the second thing is that how the just-in-time compiler actually removes that null pointer, okay, to optimize the code. Is this clear, or any question?
Yeah, got it.
Okay, just hold on for a second. I will just put the battery. All right, guys. So you must have understood some of the optimizations that we do, and the part to be happy is that these optimizations are done by even your operating system or the other languages. So if you are knowing few optimizations at one place, right, you can understand optimizations at different place. Okay, right. Like if any one of you are using the Linux operating system, probably you know that Linux operating systems work on optimization level 2. Okay, so it has level of 1, 2, and 3. 3 means highly optimized code, and 1 means actually least optimized code. So any one of you can tell me what will happen if I'll go with the aggressive optimization? What will happen if I'll run Linux on optimization level 3? Okay.
So in the past, okay, at least in Windows, okay, I've seen that okay, when we on the Visual C++ compiler, they make aggressive, they make dangerous assumptions, and I've seen some self-modifying code. Okay, prefix q was not actually expected properly, and then it led to certain bugs and all.
Right. So what you have said is correct. So what will happen if you will go on an extreme high level optimization, your VM or your operating system will crash more often, right? Because as you said that the optimizations are dangerous in nature, right? And if you will do it very aggressively, what will happen in the end, you will end up crashing your JVM, or in the end you will crashing up your operating system, right? So most of these guys will leave you on the middle level of optimizations. And if you will not do too much optimization, you will be living on the least optimizations. Things will run slower for you, right? So it is like either you drive safe on the road or you drive faster on the road, right? So if you will drive faster on the road, there is a high chances of getting accident. But if you are driving slower on the road, you will reach your destination at a higher time, right? So it is the same trade-off everywhere, right? So what you have learned is some of the optimizations that JIT compiler do, and now okay, I will show you a few more, which is interesting. Okay, so that it will give you the complete set. So you all know the multi-threading environment, right? So what happens that actually we put a synchronized block. Okay, synchronized block and all is very old concept. If you are still using multi-threading environment and you are using synchronized block, it's not good. Okay, you should use the Java util concurrent. But still, what happens? You write synchronize. You lock an object, right? 1 second. Hold on. My kids are shouting, so first I need to make them silent. Okay, guys, I'm doing a meeting. Please go to that room. Fine. So, all right, where I was, yes, I was on the multi-threading environment. So what happens that I have seen that there is a block of code which is actually not getting used by multiple thread, right? So you are just wasting your time into the synchronization block, right? Because you have written synchronization, which means that synchronization is actually a very costly affair, right? So you have seen I have written a synchronization, but it is always getting used by one of the thread only. Okay. So what I can do is that I can throw the synchronization. I will say that synchronization is not required here probably. And obviously you need to provide a path that is called uncommon trap, as you have all learned, right? And this is precisely what happens with biased locking also. So in the Java, okay, you can see my screen, right? So what I will do, I will print flags final. So what we'll do, it will print all the flags that a Java command have, and I will grep on biased. Okay. So what I missed is I missed a plus sign, right? So plus sign means you are inserting something, and minus sign means you are removing something. And I have not get anything, maybe because the B need to be small. What is wrong? Print final flags, grep biased. Let me copy it from here. Why I'm doing so much of hard work? Right. So now, yes. So you can see there is something called use biased locking, which is true, right? So biased locking is a typical thing which we use, and it says that lock need to be biased, and lock need to be biased with whom. So what we generally do is that lock need to be biased with the first thread that it used, right? So if you are having multiple threads, generally the code which has been used by the first thread, it is possible that that code that part of the block will always be used by that kind of thread only. Okay. So that is all about biased locking. So if your thread 1 and thread 2 and thread 1 have entered into the critical section first time, it will happen that most of the time thread 1 is only using the critical section. Okay, so we biased our log towards thread 1. Right. Few more optimizations are like okay, loop optimizations. If you are seeing there are two different for loop and both the loops are taking equivalent time, you can just combine those two loops. Okay, you can change your while into do while. So you should know that while is actually a costlier operation than a do while, right? Then you can reorganize your loop. All kind of things are possible, which we do in the just-in-time compiler, right? Yes. So coming to the part, these are the JVM options. You have already seen Xent, you have already seen Xcomp, you have already seen Xmixed, right? So there is something you write with your Java option that is called -client and -server. -client means you are using C1 compiler, -server means you are using C2 compiler, which is highly optimized compiler. Okay, there is something called tiered compilation, which means I will use C1 and C2 both compiler. And there used to be options like D32, D64. I think these options are still alive, but it just works on the C1 and C2 compiler. Okay. Our code base is little old. No, it's not like our code base is old, but according to us, anything which is less than 2 CPO is actually called client compiler. So in today world, almost nothing runs on the client compiler. Okay. Even your mobile don't run on client compiler because it has more than two or more cores, right? So anything which has one core, actually we say it is running by default on the client compiler. Else it will run onto the server compiler. Any questions right now?
No, so far nothing from me.
So far, no questions. Yeah. And probably you got a bit of idea also, right? What we are discussing. And I don't know why I am discussing. If you are an application developer, probably you will never use it, but it's good to understand. It's good to have the knowledge of these things. Okay. So when yeah.
Vaibhav, one suggestion. Okay, so now you have given us enough food for thought. So how will we explore it ourselves? Means, okay, is there any public domain site where we can actually get information on kind of things which we are discussing?
Yes.
So
there are a lot of ways you can explore. Depends upon your capability. So I will show you the capability number 1. So I am in the VM code. There is something called Opto folder, right? And when I'll go inside the Opto folder, you can see a lot of optimizations code that has been written. Okay, so it do graph optimizations. You can see a lot of loop optimizations, loop predicate, loop transform, loop on switch, right? You can see a huge amount of optimizations. Okay, I will take you to, this is called C1 compiler. You can go to the C1 compiler and see the things that C1 compiler do. And then you have something called compiler. No, not this compiler. Sorry, you have something called runtime, I think. Yeah. Okay. So it do all the things called what C2 compiler do. I told you that what it takes action of inlining, what it do on the basic locking, what are the compilation policy, what is the de-optimization, what is the, all kind of things will be available here, right? So you can see the caching techniques will be there. The even the loops will be there somewhere. I am 100% sure. Okay, so maybe loop is done on the C1 level only. Okay, so this is one place. This is one place where you can learn the things. And second thing is that we have some of the PDFs and white papers written on this. I will probably share on the meetup group. Okay, so there also you can go and you can see all the optimizations that has happened. Okay, now in the initial time, I told you that we will discuss about some of the real challenges that happens with this compiler, right? And even the question raised by you. So what happened is that I am working on a low latency software, like I am working for a share market rate, right? What will happen? Things are good, right? I am running all my things. My compilers are getting optimized. But you know what is the most important period for a share market? Anyone of you? Anyone of you in the share trade? No. No one of you.
Or close. Okay.
Right. No one of you.
And
No.
then
Right. I think you said it right. So you said at the starting and the closing, right?
yeah.
Right. That's true. That means you trade with the share market. Good. So okay, yes, that's good, because the most important or the most critical time for the share market is actually when it opens, right? And the first 30-second or the 40-second, actually it determines the market price. Okay. Now what will happen, that say you are running on Java compiler. So I will say that, okay, your first 40 seconds are important, but I also need the first 40 seconds because I have to optimize my compiler, right? And that's not a great idea, right? Because you cannot go for optimizing your compiler at the critical time, right? So this is the problem which generally comes with the Java application, and this is called something called slow startup time. Okay, and this is the same question which you have raised at the beginning. So we play with a lot of techniques here. Okay, we have a lot of techniques, and few techniques that we apply is that we actually supply a lot of dummy data to the share market, probably the data from the previous day. Okay, so we will say that for warming up the compiler, for making the methods hot, what I will do is that I will feed the data of the last day. Okay, so when today's share market will open, I will have all the things optimized. Okay, I will have all the methods optimized. But there is a problem in that. What is the problem in that? I generally optimize my application also in such a way that I always tell my application that you are feeding me dummy data, right? So when the data goes from dummy to real data, what happens is that your runtime compiler will say, no, it's a dummy data only. Okay, but you will say, no, this is the real data, right? So again, I have to go to the complete process of de-optimizing. Okay, so the whole idea of heating up the compiler will not work out, because here I need to de-optimize the code again to tell that, okay, this is not a dummy data and now this is the real data. Okay, what some of the JVM compilers actually do, like the Azure system C4 compiler is there, the JIT compiler. What they do is that actually they have in-memory compilation. So whatever the optimizations they do, generally they save the optimizations, and they use that optimization when the next time the server will get started. Okay, so that's also a very good technique where you can heat up your server very fast. Okay, so you can feed the data of the already in memory data. And with all these problems in JDK 9, we are coming with something called AOT, right? Some of you have said ahead of time compilation. At the starting, I have heard this word, right? So in JDK 9 and probably in the JDK 10, we are coming with ahead of time compilation, which is a compilation that happens before the runtime, right? So it is that's why it is called ahead of time compilation. It's a complicated process where actually you need to find out all the paths of the optimization. So I need to know all the paths where my source can flow in, right? And I go there and I optimize the code. So this is called AOT, which we will not discuss today. Maybe sometime else we will discuss that. It's a huge discussion again. But we are coming with something called AOT, which will definitely help us to improve the startup time. Till now, what we do is that we work with a lot of techniques to just do the startup fast. Okay, so this is something like the real application problems. Okay, so we are working on it. And my last slide will tell you about some of the benchmarking difficulties, right? So Java is actually one of the worst languages to do benchmarking. You all know what is benchmarking, right? So yes, benchmarking is a simple technique where you say that, okay, I need to understand that my method is taking how much time, or my whole execution is taking how much time, or whatever it is. So the Java benchmarking is very complicated because it behaves different when you run it from the interpreter. It behaves different when you run with the C1 compiler. It behaves different when you run with the C2 compiler, right? And actually, you don't know what is going inside, right? So what is the compiler that is running inside? And that's why most of the benchmarking, there are tools available, like we have JMM, Java Micro Benchmarking, JMB, Java Micro Benchmarking, which actually always heats up the code, right? So these JMM, when they will do the benchmarking, actually they will run your code for say 50,000 times, because they know that code is heat up and now the benchmarking will be the correct benchmarking, right? Other than your JIT compiler, the benchmarking can also be distorted by the garbage collector, because in the benchmarking we say that how much application time is actually, but garbage collector can also take a pause, right? So garbage collector actually cleans the object, right? So it can have its own pause. So that will also impact your benchmarking, right? Benchmarking can be distorted by dead code, like I told you. Benchmarking can be distorted by the wrong warm-up. Benchmarking can be distorted by the dynamic de-optimizations, like monomorphic dispatch or null pointer optimizations, right? Inlining of the code. So all these things can distort your benchmarking, right? So you should always need to use some of the tools like Java by micro benchmarking, or many tools are available in the market to do the proper benchmarking of the Java code, right? So if you really want to know that this method is taking how much time, or my complete code is taking how much time, you should go by the code. You should not go how I have written, that you will take a current dot millisecond at the top, and then in the end, and you will say, okay, I am done. This method is taking that much time, right? So like I showed you here, that's okay. So what I showed you, this. So this is actually useless. You should never do this work. Okay, you should never put a start time and end time, and never do a subtraction. Okay, this will give you always wrong result, and you have seen that, right? So when we are running our code, you are seeing how frequently we are getting the different values, right? And the values were differing by a huge number. So sometime you will get 3, sometime you are getting 14 milliseconds, sometime you are getting 7 milliseconds. So that's not a right benchmarking. Okay. These are the logging options. So when you will do log compilation, it will give you all the data value for the JIT compiler, right? And you need to unlock the diagnostic VM option. Okay, this is very important for that. Okay, some of the tools, some of the references I have put, Java performance tuning, and there is something called JIT Watch, right? So this is a third-party library which they have created, where you can see what all optimizations the JIT compiler is doing, right? And finally you should search just-in-time compiler in Google and find it out, whatever the material is that. So that's also one of the most important thing. I also blog sometime about the JIT compiler, because I work in that team closely, so I keep doing that work. Right, so I am done with the presentation. Let me know if you have any questions or any concerns or complaints or suggestions.
Okay, so I hope, okay, we'll be able to get the slides, right, in the group.
Yes, slides are already available. So you must have seen, this is a copyright of 2014, right? So because I have downloaded my previous slide, and so I will send you the link in the meetup page, right? And probably I will send you some 3-4 more talks which actually go into the detail of something. So I was not knowing that how was the listeners for the today meetup. So according to that, I probably have covered something at the very surface level. So I have not actually went into the detail that how this has been done or what it has been done. So still, I will send you all the slides.
Yeah, thank you very much.
Any other question? Any other complaints?
Thank you, Vaibhav.
Okay.
I think we may take a continued sessions on the same topic, since we have only covered the section as you mentioned.
Right, sir.
Okay. Yes, sir.
Okay, Swell. So just for your information, I will tell you that anytime you want to know about something detail in the JVM, like you want to know the detail of the garbage collector, or you want to detail on even the streams and the lambdas, how it has been written, or JDK9 features or anything, you are free to contact me. Okay, I can deliver the talk whenever you want, but this will be the mode of delivering the talk. So okay, so I am not going to come there to talk.
Okay.
Okay.
Okay, thank you.
Thank you.